Hi, my name is Shawn Hernan. I'm a security program manager here at Microsoft in the Security Engineering and Communications Group. I want to talk to you today about security testing and how that can improve your overall security posture. If you think about an application, if you think about what it is you want to ship, you've got a notion in your head, maybe captured in specs, maybe shared among the members of your team of what you intend to ship. I intend to ship software that does X, Y, and Z. That can take a variety of different forms. Hopefully it's in formal specifications that you know what it is you really want out of this. But sometimes in smaller organizations it's just shared among the people, or maybe shared among a single visionary, maybe stored in the head of a single visionary who intends to produce a product. But in actual fact, no matter what it is you intend to ship, the thing you actually ship is probably going to be slightly different. It's probably not going to have all the features you want. In the end, they're going to be slightly different. The actual software functionality is something else entirely. Now, that becomes important when you think about security testing, because now you have really three different parts of the security testing landscape. Traditional faults show up in your intended functionality, but there's also this unintended and undocumented or unknown functionality that's contained in the purely blue area. This is the place where buffer overflows and integer overflows actually show up. Nobody intends to encode that into their software as functionality, but in fact, from the attacker's point of view, that's exactly what it is. A buffer overflow is just another piece of functionality to the intruder that lets him execute arbitrary code. So that's where, from a purely functionality position point of view, that's where those functions show up. Now, thinking from a testing point of view, you really have three areas to test. You might have, your spec might have called for a certain defense. It might have called for encryption. It might have called for character scanning. It might have been called for a bunch of different things. Those defenses might, in the actual software you ship, might be missing. You might have forgotten to encrypt the output. You might have forgotten to check for a particular value of input. So you need to, for any defense that shows up in the original design, you need to have a test to make sure it's actually there. Now, you might have done it poorly. Your intended software functionality might show up in this mid-region where you might have made, for example, you might have implemented cryptography, but you might have done it incorrectly. You might have used, for example, electronic codebook mode, where you really wanted one of the feedback modes for a block cipher. So those can be difficult to detect, but you also want a test that will help you show whether or not the defense you've built, the feature you've built, is really correct. Now, I think the hardest part to test is this extra functionality area. Things that are functions in your software that you didn't intend to ship. Sometimes these take the form of Easter eggs, and there's been vulnerabilities in Easter eggs. Little interesting snippets of code that a developer might put in there for fun. There might be vulnerabilities there. More often, when we're thinking about security, these take the form of software errors like buffer overflows that permit intruders to do things that you don't want them to do. Well, how do you test for those sorts of things? Well, what intruders do is they sort of footprint your application. They take a look at an uninitialized operating system, see what's on it, and then they install your software. And then they do a diff to see what bits have you actually added to the system that they can start to go test. So now they know exactly what files you've added there, exactly what changes you've made there, and they can concentrate their security tests on just the specific things that are new to the system. What weaknesses have you introduced to the system? Well, now the attackers at least have a way to look at it. The method we use here at Microsoft to find unintended functionality in our systems is called fuzz testing. Fuzz testing is the methodical application of malformed data in a search for vulnerabilities. It is not, as some people characterize it, simply randomly throwing out simply randomly throwing input into some application. There's a method behind it, a structured way of choosing malformed data to look for particular classes of failures. And we know that it finds security and reliability issues efficiently. It turns out to be a very cost-effective way of finding vulnerabilities in our software. Even after our best code scanning and threat modeling efforts, some vulnerabilities may still remain, and fuzz testing helps us get past our preconceived notion about how the software should behave, and it puts it helps us focus on how the software actually behaves as opposed to how we think it should behave. So your first point of effort in figuring out your fuzz testing work is to find all your entry points into the code. Where can an attacker actually introduce malformed data? Your threat model should list all of those entry points. There will be things like network ports and protocols, file types and file names. They might also be things in the environment. They might be timing issues. They might be order of operation, all the places where an attacker has a choice about which code path is going to execute and what data is going to be there. Now, you may not be able to test everything from a fuzz testing point of view. Certainly, attacks by an administrator are probably not interesting to you. If an administrator if an attack would require somebody to be an administrator already, what benefit do you really achieve from a security point of view in finding a vulnerability that only an administrator could execute? So you need to rank your input levels by your entry points into your code by privilege level and accessibility. Things that are anonymously accessible by a large number of people need to be looked at first. Then things that are accessible only by authenticated users, and last, things that are accessible by administrators. From an addressability point of view, you want to look at things that are accessible remotely first, things that can be executed over the network, and then look at things that can be executed only locally. Now, keep in mind that we often fail to appreciate how much an attacker is able to influence your users into running things remotely. That shows up particularly in files. It's a very common thing, a very common attack, for an intruder to take a malformed file and send it to some of your users in hopes that one of your users will load the file into a parser remotely. So we consider files to be, in effect, a remote attack. If there's nothing requiring a file to live in an existing place and there's in a known place, and there's any scenario under which an attacker could plausibly send you a file in email, we consider that really very much a remote attack. It's a very hard thing to draw a crisp line and say things on this side of the line are local only and things on this side of the line are remote only. So be very sensitive and err on the side of believing that things can be executed remotely, even though they might design to be only executed locally. There's a tool available called Application Verifier or App Verifier that can help you find weaknesses in your code. So run your tool under App Verifier certainly. For all the file formats that you consume, and we mean for all of the file formats you consume, we certainly this is one place where you don't want to order things by the scenarios of your customers. You want to order things by anti-scenarios, by the things that the intruders will want you to do. And that means that you've got to look at all your file formats with equal levels of detail to make sure you're covering all of the scenarios there. Build a collection of valid files. First, start off collecting valid files, probably somewhere in the neighborhood of 100. If you have code coverage metrics, you want files that will give you a high degree of code coverage. You want a collection of valid files that will give you a high degree of code coverage. And then start tweaking the files at random using a tool. Now, as you become more and more sophisticated with your fuzzing efforts, those random tweaks will turn into more directed tweaks. But you never want to lose you never want to lose randomness entirely in your fuzz testing efforts. One of the benefits of fuzzing is precisely that it gets you out of your own preconceived notions about how an application is supposed to behave. So always incorporate some degree of randomness in your fuzzing, but you will certainly find that in order to achieve the code coverage numbers you want, you will have to make selected changes to files to exercise a block that might not get exercised through random chance alone. Then load the file into your application, that is, load the malformed file into your application, and observe what happens. Does it crash? Is there a memory spike? Is there an access violation of some kind? Many of those failures very frequently correspond directly to vulnerabilities that an intruder could exploit. If you have a write access violation in one of the malformed files, or rather the malformed files uncover a write access violation in the parser, then you almost have certainly a directly exploitable vulnerability in your system that needs to be corrected pretty quickly. For network-facing things and for things in general, build a rogue client or server. Don't rely entirely on your own pre-existing client or server, in part because the clients and servers tend to produce correctly formed data according to the protocol. They tend to, on the client side or the server side, format the data in an expected fashion before sending it to their their peer on the other side of the connection. So if you're relying on the tools you've built to test a client or a server, then you might run into problems. So build a rogue client or server, perhaps in an entirely different language. Sometimes, if you've written something in C or C++, consider writing an implementation in Python, for example, specifically as a way to get past your preconceived notions about what it's supposed to do. Now, it doesn't need to have all the functionality. All it needs to be able to do is deliver bits according to the protocol. But if you rely on your own code, that might lead you down a garden path. Now, when you're thinking about how do you go about changing a file in a random way, one simple way is to just write a random series of bytes. You'd be surprised how often writing a random series of bytes in an otherwise valid file will cause an application to crash. Now, again, I want to stress the idea that if, as you begin this fuzzing work, one of the things that your developers and testers might tell you is that's not a security issue. They'll tell you that users won't create, there's no way for a user to create a file that looks like this. Well, in fact, an attacker is perfectly free to create a file that looks any way he wants it to look. And he can send it to your users, and through just a trivial amount of social engineering, get one of your users to execute that file or to load that file in a vulnerable parser. So it's really very critical that you don't fall victim to the trap, that you don't fall victim to the thought that that nobody else could produce a file that looks like this. So write a random series of bytes. Flip two adjacent bytes. Look for ASCII and Unicode text and set the trailing null to a non-null. That makes the string be very long. Set size values to random numbers, and if those values are integer values, set them to a negative number. Set them to 0. Set them close to max int or min int. Certainly look for corner cases. Look for values near the extremes. All of the good testing procedures you have, you should bring to bear on fuzz testing. But you should certainly allow randomness to play a part in that. Now, I said this before, that when you're considering network fuzzing, you want to build a rogue front end to your application on both the client side and server side. And you can tweak bits according to rules that you will develop as you get more sophisticated, both as they leave the client and enter the server, or leave the server and enter the client. And don't leave out client-side attacks. Don't leave out the possibility that someone may have built a malicious server to which they will draw your users using a vulnerable client. So test the client every bit as hard as you would test the server. The big rule, the thing you want to take away from this, if nothing else, is there are no rules for the attacker. No matter how how strict you think the protocol is, no matter how complex you think a file format is. An intruder is under no obligation whatsoever to follow any rules that you've set. They're free to provide any old data you want, and that includes on authenticated interfaces. Sometimes we see teams fall into the trap of believing that, well, this interface here is authenticated, so therefore nobody can attack it. Only valid users can execute it to begin with. But in fact, every authenticated interface takes some unauthenticated data to start with, namely the certificate or password or connection or pipe or whatever it is the authentication data is, no matter how the authentication data is getting to the service, there's always going to be something to check the authentication data, and that's a great attack point for attackers. So if you provide a client access to the server, don't use it. Mimic the client in code. If you rely on a specific service, build a bogus one. Don't use your own assumptions when doing fuzz testing. If you're consuming files, try device names, try ... try unusual paths, try places that the intruder shouldn't get to. Include directory limiters and all of the file name separators in your code. Look for hangs, accesses to other files, accesses to directories, to registry entries that shouldn't be there. Fuzz all the data structures. Look for access violations or memory leaks. App Verifier can help you there. Memory spikes very often correspond to integer overflows. It's a very common paradigm for tools to read an integer out of either a file or a network stream and use that as a size of a data structure. So if you're seeing a memory spike, that is a large allocation where you're expecting a small one, that might correlate very well to an integer overflow. Look for any personally identifiable information in any of these scenarios. That might mean you have a privacy issue on your hands. So if you've got privacy concerns on top of this, information disclosure threats might, depending on what space you're operating in, might be even regulated. So you need to look for personally identifiable information and treat those situations very carefully. One thing that I've always found effective is looking for should, assume, undefined, we expect, we think, anything like that in the code or in the documentation that that leads you to an undefined scenario or puts the burden of checking on somebody else. If you run across code that that says, well, we assume that the input will be no more than 50 bytes here, that's almost certainly a vulnerability. This should arrive in this order. We're not checking this. So the comments and the specs can give away pretty easy opportunities for you to find vulnerabilities. ActiveX controls are an especially rich target to fuzz test, especially the things marked safe for scripting. Look at each property and method and ask yourself, what could a bad guy do here? Certainly don't produce a safe for scripting control that doesn't give you, if you can't tell who's calling it, if you've got no authentication mechanism, all of the things that a safe for scripting control can do must be safe for anybody to execute. So ActiveX is a great and rich opportunity to fuzz. Now, you also want to fuzz data that crosses privilege elevation boundaries. So if you consider a scenario like this where you're pushing data from a lower privilege process into a higher privilege process, well, the admin might have full control on a data store and allow everyone to read that data. But what happens if you have a situation where everybody can write some data and you have a high privilege process reading it? That's not an uncommon place. That's not an uncommon scenario. Logging systems, for example, permit a lot of people to be able to write to the logs, but only administrators or privileged processes to be able to read from the logs. Data entry systems, accounting systems, antivirus systems or other system scanning utilities frequently run at elevated privilege and consume data that everybody can write to. So fuzz all of those interfaces locally and remotely wherever they exist. So from a security testing checklist point of view, use fuzzers for all your consumed resources, files, network protocols, timing interfaces, environment variables, everything you have there. At a minimum, you should look at 100,000 iterations per data type. That's probably the minimum acceptable range when you're looking at fuzz testing, and that can be a significant amount of work, so certainly build it into your schedule. And use tools to do this. There are tools available, and in fact, this book includes a fuzzer as part of the material. That will help get you started with fuzzing. There are tools available on the network to help you fuzz, and certainly investigate those. But consider what an attacker has available to him. Fuzzing is one of the best methods we know of for an attacker to find weaknesses in your program. If you can take that method away from the attackers, then you will have all the cards. You will hold all of the techniques that the attackers hold, and then you should be able to, with all the additional resources you have, additional insight into your own systems, knowledge of its design and architecture and security training, you should certainly be able to drastically reduce the number of vulnerabilities shipping in your product.